Hello and welcome back. I'm Matthew Lay, and today we are going to study parallel circuits. In this lesson, we have some objectives. First, we want to define a parallel circuit. Next, we want to list the characteristics of that parallel circuit. And we want to be able to calculate total circuit resistance, current, and power of a parallel circuit. We're going to see that that is different from how we did it for a series circuit. And we want to be able to calculate branch currents and the power dissipated for each branch. That's a new term which we're going to study the terms of a parallel circuit. And then we want to define the open circuit as it applies to the parallel circuit and the short as it applies to our parallel circuit as well. So let's get started here. So this is our exercise that we did in the series circuit lesson. That we have two components. What are the two different configurations that we can make? One is the series circuit, which we've already studied. The other is this parallel circuit. And that's what we are going to be studying today. So let's talk about some terms here. The parallel circuit is comprised of, in this case, two components that the beginning of each component is connected to the same point electrically, meaning that the beginning of this resistor and the beginning of this resistor are all the same point electrically, meaning if I, anywhere on here, I would experience the positive of the battery anywhere on that line. And down here, the other end of each resistor is connected to the same point electrically as well, and anywhere along this connection would be the same as being connected to the negative of the battery. So we use the term that they are the same point electrically. So that's one term that we need to learn. So just proving this out, if I take a meter and I put one end on the negative of the battery and the other end at point A there, the top of resistor 1, I am going to measure whatever my total voltage is, because you can see here that that would be the same as just putting the meter across my power source. Now, if I take that meter away and I move it over here to the beginning of resistor 2 or point B, we will see that we still are connected to the same point here at the top of the battery. So I'm going to measure the top of that power source, or I'm going to be measuring across that power source, and whatever that power source equals is going to be what that measurement is at point B. Okay, so since point A and point B are both equal to our total voltage in this circuit, we say that they're the same point electrically. So now if I come down here and I take my meter and I hook it to the negative of the battery and I hook it down here to C, you notice there's nothing, there's no place for any voltage to drop, there's no resistance there. So that is going to actually measure 0 volts, okay? Now, if I move the meter over here to my ending of my second resistor, which is at point D there, I'm also going to get 0 volts, because it'd be like having two leads of the meter on the negative of my power supply, and we're not going to get any potential difference across the power supply, because we're physically not measuring across the power supply. We're measuring the same point on the power supply. So therefore, since they're both at 0 volts, both at the negative of the power supply, we say they are the same point electrically. So that's where that term comes from, meaning the same point electrically. They're electrically at the same point on the circuit. Okay, so let's look at voltage. The voltage in a parallel circuit is common across all components. Now, this is different from a series circuit. Remember, a series circuit was a voltage divider. Now, all these components are going to experience the same voltage because they're all across our power supply. Okay, so our total voltage is going to be equal to the voltage that we experience across R1 and the voltage we experience across R2. So all three of those are going to be the same voltage. So if our total voltage is 20 volts, the voltage across R1 will be 20 volts, and the voltage across R2 will be 20 volts. Okay, look at some more terms here. This is called a branch. Now, this is a very simple branch because it only has one resistor, but when we get into more complex circuits, we're going to see that we can have multiple components in one branch. And there is our second branch. So this parallel circuit has two branches. Of course, we can add more resistors and make more branches in our circuit just by adding more components. Okay. Here is a way that we can denote branches as well as just saying the R1 branch, because it could have more than one resistor in it. So we can use node letters. Remember, we talked about this with voltage referencing. This little dot here with a letter next to it is considered a node or a point on the circuit. So the first branch here, R1, is going to be branch AB. The second branch, R2, is going to be branch CD. So let's look at how this can be used in denoting currents on the next slide here. Okay, so a parallel circuit is not a voltage divider. We found out that it has a common voltage across all components, but it is considered a current divider because current is divided among the branches. We're going to see that here. So the branch current can be calculated using Ohm's law. Okay, so EA or IAB, so that's talking about this branch right here. We're defining that branch as sub AB. Will be equal to our total voltage, because remember, each one of these branches has total voltage across it, and then the resistance across RAB. Now, the resistance across RAB currently is just one resistor, but it could be multiple resistors. In the future, it will. The current on branch CD is, again, that total voltage, because voltage is common in a parallel circuit, and it's going to be divided by the resistance in that branch, RCD. And the total current that comes out of this power supply is the sum of those two, because the total current is divided amongst those two. A parallel circuit is a current divider, and so it's going to divide that current among those two branches. Okay, so I total is going to be the branch current in branch AB plus the branch current in branch CD. Okay, so that current plus that current right there equals that total current. So the total current is going to flow in here. This is conventional current flow. It's going to flow in here, and it's going to flow back to the power source here. Okay, at point A is where it divides. Part of it's going to go this way, and part of it's going to go that way. And the length of these arrows, if you add those two together, you're going to get this. So these two resistors would have to be equal to each other to have the same current through each branch. So let's look at Kirchhoff's current law. We've studied Kirchhoff's voltage law in the series circuit presentation. Kirchhoff's current law is similar, but it has to do with currents instead of voltage. So the point A is what's termed a node, and any node in an electrical circuit, the sum of the current flowing into that node must equal the sum of the current flowing out of that node. So here I'm showing this current IA coming into node A, and then it branches out to these two nodes here, and then it comes back through B here. So we're going to see how that applies. So the current IA, which is the current flowing into node A, is going to equal the current that flows through R1 and through R2, because it's divided at this point. Okay. We can also say that the current flowing into node B, which would be this current coming through R1 and this current coming through R2, they meet at this point and they come out of node B right here. That's why I have I sub B. To calculate the total resistance of a parallel circuit, we must first explore a new quantity called conductance. Conductance is nothing more than the opposite side of resistance. Okay, so conductance is the ease at which electrical current can flow through a component instead of how difficult it is for the resistance to flow. And conductance, we use the letter G in our mathematical formulas, and the unit of measure is Siemens. Siemens was the gentleman who actually invented the electric generator, and so there's actually a whole company named after him that's still very popular today. But the System International unit, remember that's the metric system for conductance, is measured in his honor. So conductance can be calculated by taking the multiplicative inverse of the resistance value. Taking the reciprocal is the multiplicative inverse is a fancy way of saying taking the reciprocal. So G just equals 1 over R. Okay, so let's look at our inversion calculation here. To take the inverse of 220 ohms, I'm going to just show you how to do that on the calculator. So you want to enter your 220, and then there's a button that says x to the minus 1. X to the minus 1 means 1 over, or 1 divided by the number that you just put in the calculator. And then you press the equals button, and you will get the reciprocal for 220 ohms, which is 4.545 millisiemens. Okay. Now we're going to use this when we're going to calculate our total resistance for a parallel circuit. So total resistance for a parallel circuit. To calculate total resistance, the conductance method is used. Okay. The total resistance can be calculated by inverting the total conductance of the parallel circuit. So we have to find individual conductance of each resistors, add those together, and then invert that number. Okay, so RT equals 1 over GT. Okay, total resistance equals 1 over total conductance. The total conductance is the sum of all the branch conductance values. Okay, so G total is the same as the reciprocal of R1 plus the reciprocal of R2. Therefore, and we can punch it in our calculator this way, RT equals 1 over R1 plus 1 over R2. Okay, we're going to go through an example to show you how to do this. Okay, so if we have 100 k ohms and 200 k ohms, what we would do is calculate it this way. We would say 1 over 100 k ohms plus 100 or 200, 1 over 200 k ohms. Okay. On the calculator, you'd enter the following. Okay. Now this, if you have the newer calculator, it's a little bit different. So you would, on the older calculator, it's 100 shift 6. That puts it into K. You'd have to hit 100 option 3 and then select K instead of the shift 6. Then you would hit the reciprocal button, the x to the minus 1. Then you would say plus, and you would say 200. And on the new calculator, you would say option 3 and then select K. Then hit the x to the minus 1 button again and hit the equal sign. And when you get the equal sign, that will give you the conductance, the total conductance of the circuit. Then if you press the x to the minus 1 button one more time, that'll take the reciprocal of the total inductance and give you total resistance. Okay. And so if you punch that in properly, your total resistance will be 66.667 k ohms. Okay. Now, if you notice, the total resistance is lower than any one of the individual resistor values. So that's a quick check. If you get a value that's higher than any one of the individual resistors, then you've calculated something incorrectly. So this is something to note. The total resistance will always be smaller than the smallest resistor in a parallel circuit. Okay? Okay, let's look at power as it applies to our parallel circuit. Okay, the power dissipated by each component can be calculated by squaring the total voltage and dividing by the branch resistance. Okay, total voltage is going to be the same across all the components, and then the branch's resistance will give us the power in that branch. Okay, so since we only have one resistor in this branch, we're going to go ahead and call it P sub 1 for the power in R1, and it's going to be our total voltage squared. Remember, our total voltage and E sub 1 is the same thing because voltage is common in a parallel circuit, and divide that by R1. And for the second branch, P2 is going to be E total squared divided by R2. So let's look a little bit further about total power. So total power is equal to the sum of all the branch circuits power that gets dissipated in each one of those branches. So the total power is going to equal the sum of the power in branch AB and branch CD. Total power can also be calculated by multiplying the source in the total current. The total power equals the total current times the total voltage as well. Okay, let's look at how a short affects a parallel circuit. In the above circuit, the second branch has been shorted. We can see that here. Okay, so if that gets shorted, we'll have total voltage. Remember, voltage is common across each one of these branches with no resistance. And luckily we have a fuse here that's actually going to pop that fuse. Since the short negates any resistance in branch 2, the current will increase until that fuse actually blows. The current flowing through branch 1 and branch 3 will not be affected by the short in branch 2. Okay, and this happens in your home. You have multiple circuit breakers in your house. If you have one branch that is overloaded and you pop a circuit breaker, it doesn't kill the whole house. It's only going to kill everything that's in that branch. Okay. Let's see how an open is affecting our total power output and the other branches as well. So now that we shorted that component out, that R2, we have a blown fuse. In the above circuit, branch 2 has a blown fuse now, and the current will still flow through branch 1 and branch 3. Remember, if we blew a fuse in a series circuit, it killed everything in that circuit. Well, that's not going to be true for a parallel circuit. Branch 1 and branch 3 still have total voltage across it, and the resistance is still good because the fuses are still good. We are going to have current through those two branches. The total current will decrease, however, because only two branches are now pulling power from the power source, and the power will decrease because there's less current draw from the power source because we have one less branch drawing current. Okay. You can measure total voltage across that blown fuse in branch 2. It would be total voltage. Remember, if we put that meter across there, it's going to put 10 mega ohms of resistance in that branch, and 99.9% of the voltage drop is going to be across the meter, and therefore it will show the source voltage, and you know that you have a blown fuse then without even having to pull the fuse out of the circuit. Okay, so let's review here. Define a parallel circuit. So if you want to pause and then come back. Okay, so a parallel circuit, we can define it multiple ways. It is a current divider. It has multiple paths for current to flow. That's why it's called a current divider. Each component experiences the same or source voltage. So the voltage is the same across all of those. Resistance, the total resistance, is the inverse of the total conductance of the series circuit or the parallel circuit, and power is additive still in a parallel circuit. So a series circuit and a parallel circuit, power is additive in both of those. That's the one common between the two. So we just did list the characteristics of a parallel circuit. It's current divider, voltage is common, resistance is the total resistance is the inversion of the total conductance of the circuit, and power is additive. Okay, so calculate circuit resistance and total current and power for a parallel circuit, and I have some givens here for you. And if you want to go ahead and calculate those, we'll come back with the answers. And then we want to be able to calculate our branch circuits and the power dissipated in each branch. The effect of an open on a parallel circuit is that branch is not conducting current anymore, so we're going to decrease in power output and decrease in current output, but the other branches will still have current flow. A short is going to be the opposite. A short is going to increase the current to a point where some sort of overload protection is going to have to take over, whether it's in the power supply, we pop a fuse in the power supply, or if we have branch circuit fuses, we will see the effect in a blown fuse. Let's come and calculate out this example that I gave you. So first thing we want to do is find our total resistance. Okay, so if I take the reciprocal of 120, so that's 1 divided by 120, and I add that to the reciprocal of 1 divided by 180, that value right there is my total conductance, and it would be what, 13.888 millisiemens. Okay, but then I want to take the reciprocal of that. Okay, so I am going to store that in my memory, and then I'm going to say 1 divided by that value. Okay, so I'll come back here. And there is my total resistance. It's going to be 72 ohms. Okay, so our quick check, 72 ohms is going to be less than any one of my branch resistance, so that looks good. Okay, so now to get my total current, I'm going to take 10 and I'm going to divide by my 72 ohms. Okay, so my current, I'm going to multiply by 1,000 here to put it into milliamps, is going to be 138.889 milliamps would be my total current. And then we could do individual currents very simply by just saying 10 divided by 120. So that would be 83.333 milliamps, and my 10 divided by my 180. That would be 55.555. So if I take 55.555 and I add that to 83.333, I get that 138.888 that we calculated using the reciprocal method with total conductance. Okay, and then we can get total power just by multiplying this. This is my total current, and I can just multiply that times my total power. And so I actually get 1.388 watts, because that was the 13.88 was milli. So I'd have to divide by 1,000 to. So it's 1.389 watts for this circuit. Okay, so there's all the calculations for our actual givens here. Okay. So this concludes our lesson on parallel circuits. I hope that was helpful, and we'll see you in the next video.